Hi everyone, Mrs. Basega here, and today we're going to work on applications. I just had you working on finding the x and y components using sine and cosine. So what are we going to do with them? Well, let's say we have a situation where I'm giving you a challenge to find the missing weight and mass of some unknown object. Right? So let's say I know T1 and T2. I've got their angles, I've got some force probes to measure them, and your goal is to find the missing mass and weight. Your first step is going to be to resolve T1 and T2 into their components. Let's start with T1. T1 is at 80 degrees above the horizontal, and let's say my force probe along that string reads 10 newtons. In the y direction, I would want to use sine to calculate that component. In the x direction, I would use cosine. For notation, notice that I use T1y to be the y component of T1. So that's 10 sine 80 degrees, or in this case, that's 9.84 newtons up. In the x direction, T1x is T1 cosine 80 degrees, or 10 cosine 80, which is 1.736 newtons right. Now we're going to hold on to these two numbers right here, and we're going to substitute them back into our free body diagram in just a second. So hold on to them. So next, let's do the same thing with T2. T2 was at a much lower angle, it was at 20 degrees, so it's going to have a much lower force. Let's say we connect our force probe and the force probe reads 1.85 newtons to the right. T2x then is T2 cosine 20. That's 1.85 cosine 20, or about 1.73 newtons to the right. T2y then would be our T2 sine 20, or in this case 1.85 sine 20. And that's really small. Because it's a low angle, it only is going to take some of the weight. T2 is not going to be really helpful in holding up the weight of this unknown object. Next step, let's redraw our free body diagram. We didn't know the weight, but now we're going to take the y components as calculated from earlier. T1y was 9.8 something newtons up, and T2y was 0.63 newtons up. T2x was 1.7, oh, where's my hand going? 1.73 newtons to the right. And when you do this in real life, you'll see that sometimes the tensions are a little bit off, but if you know they're in equilibrium, you can say that's close enough. So in the x direction, equilibrium. In the y direction, equilibrium means that the weight of the object is 10.47 newtons down. I would take my two components in the y direction and add them together. Finally, let's calculate the mass by dividing by 9.8 on both sides to get 1.06 kilograms. So let's look at a non-numerical example. And overall, it'll explain why we do the things we do. Let's say we have a normal force, friction force, and an applied force that's up at an angle. I would redraw my free body diagram to simplify my forces. Instead of having that weird force up at an angle there, I would take FAY's component, that's FA sine theta, and FAX's component, that's FA cosine theta, and I would be able to apply equilibrium conditions from perpendicular vectors. Equation-wise, in only this scenario is this true, that the friction force is equal to FA cosine theta, and in the y direction, FA sine theta plus normal equals gravity. The reason I say this is only true in this scenario is if we change the direction of the applied force or the tension forces, those equations would change. So now we've looked at one quantitative, that is one numerical example, and one symbolic example. Let's have you try this on your own in a lab setting. Best of luck.